The first-generation ship will be humanity's greatest achievement. It will also be its cruelest experiment. Thousands of people locked inside a metal cylinder, launched into centuries of darkness toward a star they'll never reach. Because somewhere between launch and arrival, something always goes wrong. If you want to join me on more journeys, please subscribe to the channel. You'll be the first to know when we uncover the next cosmic mystery. Now let's get started. Imagine boarding a vessel knowing with absolute certainty that you will die in space. Not in a tragic accident, but simply because the journey is longer than your life. Your purpose isn't to arrive. Your purpose is to raise children who will raise children who will raise children, maintaining a tiny bubble of humanity through the cosmic void, preserving the mission for people you'll never meet. This is the psychological contract of a generation ship, and it's the first crack in the foundation. But we'll return to that later. Let's talk about what scientists and engineers are actually proposing when they design these vessels. One of the most comprehensive attempts to blueprint a real generation ship is Project Hyperion, an initiative led by the Initiative for Interstellar Studies. Their design envisions a massive structure, potentially based on concepts like the Stanford Torus, a rotating space habitat that uses centrifugal force to simulate gravity. Why rotation? Because extended exposure to microgravity causes devastating effects on the human body. Bones lose density at a rate of 1 to 2% per month in zero gravity. Muscles atrophy. Cardiovascular systems weaken. Fluid shifts toward the head, causing vision problems and potentially increasing intracranial pressure. Astronauts on the International Space Station exercise for 2.5 hours every single day to minimize these effects, and they still return to Earth weakened, requiring months of rehabilitation. Now imagine living your entire life in microgravity. You'd be born with bones that never properly developed, muscles that never strengthened against resistance. You might never be able to walk on a planet with Earth-like gravity. The rotating habitat solves this by creating artificial gravity through rotation, pressing occupants against the outer ring of the structure through centrifugal acceleration. But here's where the engineering challenges begin to pile up like snow in a blizzard. A Stanford Torus design, one of the more modest proposals, would need to be enormous. We're talking about a structure roughly 1.8 kilometers in diameter, rotating once per minute to produce Earth-normal gravity at the outer rim. The mass of such a structure, even with advanced materials, would be staggering. Current estimates suggest something in the range of 10 million to 30 million metric tons, though some designs push far higher. Where do you get that mass? You can't launch it from Earth. The cost would be astronomical, requiring hundreds of thousands of rocket launches. Instead, you'd need to mine asteroids or the moon, constructing the vessel in space using raw materials harvested from celestial bodies. This alone would require decades of infrastructure development, a space-based industrial revolution that hasn't even begun, and we haven't even talked about propulsion yet. How do you move something that massive through interstellar space? Chemical rockets are completely inadequate. The amount of fuel required would exceed the mass of the ship itself by orders of magnitude. Nuclear pulse propulsion, the concept of detonating small nuclear bombs behind a massive pusher plate, was seriously studied in Project Orion during the 1950s and 60s. It could theoretically achieve speeds of several percent of light speed, potentially cutting a journey to Alpha Centauri down to a century or less. But it requires detonating thousands of nuclear devices, raises enormous questions about radiation shielding, and is currently banned by international treaties. Ion drives and other electric propulsion systems are efficient but provide minuscule thrust, taking years just to accelerate to modest velocities. Advanced concepts like fusion rockets remain theoretical, with controlled nuclear fusion still eluding us despite decades of research. Speaking of the cold, hostile nature of space, you need to understand just how lethal the environment between stars truly is. If you're curious about the extreme temperatures and dangers lurking in the void, I covered that in detail in my video, The Terrifying Truth About How Cold Space Really Is, on the card above, where we explore what happens to matter in the near absolute zero conditions of deep space. It's directly relevant to understanding the challenges these generation ships would face, so check that out after this. Now let's assume for a moment that we solve the construction and propulsional problems. We've built our massive rotating habitat, fitted it with some kind of advanced propulsion system, and prepared it for a 250-year journey to a nearby exoplanet. Now comes the question that turns out to be far more troubling than anyone initially realized. Who goes aboard and how many people do you need? This isn't a trivial question. It's actually one of the most critical variables in the entire equation, and recent research has revealed some deeply concerning answers. You can't send just a handful of people. Small populations face genetic bottlenecks. With too little genetic diversity, you'd see inbreeding, the expression of harmful recessive genes, and a cascade of health problems over generations. Conservation biology has taught us brutal lessons about minimum viable populations. For animal species, scientists estimate you typically need at least 500 individuals to maintain genetic diversity and avoid extinction from inbreeding depression over long time scales. But humans are more complex than most animals. We have cultural requirements, social needs, specialized knowledge that must be preserved and transmitted. We need teachers, doctors, engineers, farmers, psychologists, and countless other specialists. We need enough people that children have peers, that adults have social networks, that the society doesn't collapse into dysfunction from isolation or conflict. Early estimates for generation ship populations were wildly optimistic. Some science fiction suggested crews of hundreds, but when scientists actually ran the numbers using population genetics models and computer simulations, the results were sobering. Research conducted by Dr. Frédéric Marin at the University of Strasbourg used an agent-based Monte Carlo code called Heritage, which simulates human evolution within restrictive environments like generation ships. This wasn't guesswork or speculation. This was rigorous computational modeling that incorporated the actual human genome with 46 chromosomes, 2,110 genetic loci, and realistic models of meiosis, genetic drift, and mutation. What did they find? For a journey lasting around 250 years, you'd need a starting crew of at least 500 individuals to maintain genetic viability under ideal conditions. But here's the catch, that's under ideal conditions. That's assuming perfect genetic screening before departure, no major disasters, stable population numbers, and most critically, effective protection from radiation. Change any of those variables and the numbers get worse, much worse. Let's talk about radiation, because this is where the generation ship dream starts to crumble into a nightmare. When you're on Earth, you're protected by two extraordinary shields that you probably never think about. The first is our magnetosphere, an invisible magnetic bubble generated by the churning iron core of our planet. It extends thousands of kilometers into space, deflecting charged particles from the solar wind and cosmic rays. The second is our atmosphere, a 100-kilometer thick blanket of gas that absorbs and scatters radiation before it reaches the surface. Together, these shields reduce the radiation dose you receive to negligible levels, around 2 to 3 millisieverts per year from natural background radiation, depending on where you live. Now imagine you're in deep space, in the vast emptiness between stars. There's no magnetosphere, there's no atmosphere. You're exposed to the full fury of the cosmos, and that fury is relentless. Galactic cosmic rays, high-energy particles accelerated to near-light speed by supernovae and other violent astrophysical events, constantly bombard your ship. These aren't like the gentle photons of visible light. These are atomic nuclei, stripped of their electrons, traveling at relativistic velocities with enough energy to punch through meters of solid material. When they strike atoms in your ship's hull, they create cascading showers of secondary particles, a spray of radiation that propagates through your vessel. Then there are solar energetic particles, though you'd be beyond the main influence of our sun on an interstellar voyage. But the background cosmic ray flux never stops. Never. It's one of the fundamental hazards of existing in space. And here's what makes it truly insidious. This radiation damages DNA, not might damage, does damage, constantly. Every time a high-energy particle passes through a living cell, it can break chemical bonds, create free radicals, and directly damage the DNA molecule. Your cells have repair mechanisms evolved over billions of years to handle the low-level radiation exposure we experience on Earth. But those mechanisms were never designed for the radiation environment of deep space. They can be overwhelmed, and when DNA damage accumulates faster than some cells can repair it, you get mutations. Most mutations are neutral or harmful. A tiny fraction might be beneficial, but on a generation shift over centuries of exposure, the mutation rate increases dramatically compared to Earth baseline. Dr. Marin's research team incorporated radiation effects into their heritage simulation model. They modeled what happens when cosmic ray bombardment causes neomutations, new genetic changes that weren't present in the original population. And they studied how these mutations affect phenotypes, the actual physical characteristics of individuals, including life expectancy, fertility, pregnancy success rates, and miscarriage rates. The results were published in 2025 in a paper titled Genetic Evolution of a Multi-Generational Population in the Context of Interstellar Space Travels, Part 2, under scenarios with adequate shielding, where the ship's hull design successfully protects the crew from the worst of the radiation environment. The results aligned with the neutral hypothesis. For crews of around 500 people, genetic diversity remained relatively stable over centuries. Allele frequencies didn't drift too dramatically. The population remained viable. But here's the terrifying part. When they modeled scenarios where shielding failed to adequately protect the crew, where radiation levels were fixed at extreme levels or increased over time due to shield degradation, everything fell apart. Shield degradation is a realistic concern, by the way. Space isn't empty. It contains dust, microscopic particles that would impact your ship constantly over centuries of travel. Each impact erodes the hull incrementally. Radiation itself can damage materials over time, making them brittle or altering their structural properties. And if your shielding begins to fail even slightly, radiation exposure increases. As exposure increases, mutation rates climb. As mutation rates climb, you start seeing increased miscarriages, reduced fertility, shortened life expectancies, and higher rates of genetic disorders. The simulation revealed a horrifying positive feedback loop. As radiation-induced mutations accumulate, population health declines. As health declines, fewer healthy children are born. As fewer children are born, population numbers begin to shrink. As the population shrinks, you lose genetic diversity faster. As you lose genetic diversity, the effects of inbreeding intensify. Harmful recessive genes begin expressing more frequently, and the spiral accelerates. In the worst-case scenarios modeled, a generation ship population could collapse entirely within a few centuries, never reaching its destination. The ship continues flying through the void, its trajectory unchanging, but inside, the inhabitants have dwindled to non-viability, perhaps dying out completely, leaving empty corridors and silent hydroponics bays. A tomb sailing between the stars. But let's back up and assume we've solved the radiation problem. Let's say we develop shielding technology far beyond our current capabilities, perhaps using meters-thick layers of water or polyethylene, or active magnetic shielding that creates an artificial magnetosphere around the vessel. Let's grant that optimistic assumption. We still have another catastrophic problem: life support. A generation ship must be a completely closed ecological system. Unlike the International Space Station, which receives regular resupply missions from Earth, a generation ship is utterly alone. Once it leaves the solar system, there's no turning back, no emergency resupply, no rescue mission. Everything the crew needs to survive for centuries must either be brought along or recycled with near-perfect efficiency. Let's start with water. An adult human needs roughly 2 to 3 liters of drinking water per day. You also need water for hygiene, for growing food, for industrial processes. A single person on Earth uses somewhere between 200 and 300 liters per day when you account for all uses, though on a generation ship, you'd minimize this drastically through aggressive recycling. But even if you reduce it to 50 liters per person per day, which would require reusing water for multiple purposes and achieving extremely high recycling efficiency, you're looking at enormous volumes. For a crew of 500 people, that's 25,000 liters per day, or 9.125 million liters per year. Over a 250-year voyage, that's 2.28 billion liters, assuming zero loss, but there will be loss. Recycling is never 100% efficient. Some water will be lost to leaks, to chemical reactions that bind hydrogen and oxygen into other compounds, to waste products that can't be recovered. You need reserves, you need redundancy. The mass and volume requirements are staggering. Now consider air. Humans breathe oxygen and exhale carbon dioxide. On Earth, plants and photosynthetic organisms recycle carbon dioxide back into oxygen through photosynthesis, part of the natural carbon cycle that sustained life for billions of years. On a generation ship, you'd need to recreate this cycle artificially. You could use plants, growing them in large-scale farms that convert carbon dioxide to oxygen while simultaneously producing food. But plants require light, water, nutrients, and space. They're also vulnerable to disease. A blight could wipe out critical crops, causing both an oxygen production crisis and a food shortage simultaneously. Alternatively, you could use chemical or electrochemical systems to split carbon dioxide back into oxygen and carbon. The International Space Station uses such systems to supplement oxygen production, but these require significant energy input, and over time, you accumulate carbon that must be stored or used somehow. Nothing is free. Every solution creates secondary problems. Food is perhaps the most complex challenge. Humans need a diverse diet to remain healthy. Proteins, carbohydrates, fats, vitamins, minerals, trace elements. You could bring frozen or preserved food for some portion of the journey, but the quantities required for 500 people over 250 years are prohibitive. You'd need roughly 300,000 to 400,000 metric tons of food, depending on caloric requirements and preservation efficiency. That's an enormous mass fraction of your total ship mass, and it solves nothing because eventually it runs out, so you must grow food aboard the ship. This means establishing functioning agricultural systems in a closed environment. You need soil or hydroponic systems, seeds, carefully controlled lighting that mimics the solar spectrum, temperature regulation, pest control, pollination. Many crops require insect pollinators like bees. Do you bring bees? Do you hand pollinate thousands of plants? What happens if a critical crop fails due to disease or environmental imbalance? Do you have genetic backups, seed banks, the knowledge to cultivate alternative crops? And here's something most people never consider. Soil is alive. Healthy agricultural soil contains billions of microorganisms per gram, bacteria, fungi, protozoa, nematodes, all working together to break down organic matter, cycle nutrients, and support plant growth. Can you maintain that living soil ecosystem for centuries in an artificial environment? What happens when the microbial populations drift, when certain species die out and others dominate? Can you rebalance it? Do you have the expertise? This brings us to knowledge preservation, one of the most underappreciated challenges of generation ships. Your initial crew might include world-class experts, agronomists, engineers, physicians, geneticists, physicists, but those experts will die within the first few decades. Can they fully train the next generation? Can knowledge be passed down reliably for 10 or 20 generations? Think about how knowledge is maintained on Earth. We have universities, libraries, the internet, massive redundant systems for preserving information. We have specialization. If you need an expert in a narrow field, you can find one among Earth's 8 billion people. But on a generation ship with 500 people, you can't have that level of specialization. Everyone must be generalist to some degree. You might have one person who knows hydroponics, one who understands the ship's reactor, one who can perform surgery. What happens when that person dies unexpectedly? What if they die before fully training their replacement? There's also the problem of technological decay. Your ship is filled with incredibly complex systems, many of which cannot be replaced. The propulsion system, the reactor, the life support infrastructure, the computers. These were built on Earth using Earth's industrial base. You can't manufacture replacement computer chips on a generation ship. You don't have the clean rooms, the lithography equipment, the supply chain. So when systems fail, and over centuries they will fail, you must repair them with what you have. You scavenge parts from less critical systems, you improvise, and with each improvisation, the ship becomes a little less capable, a little more fragile. Engineers call this graceful degradation, when systems decline gradually, losing functionality incrementally rather than failing catastrophically. But there's nothing graceful about watching your only home slowly fall apart around you, knowing you lack the tools to properly fix it, knowing that each generation inherits a slightly more decrepit vessel than the last. Now let's talk about the psychological dimension, because this is where generation ships face perhaps their most insurmountable obstacle. Human psychology evolved on Earth, in tribal groups ranging from a few dozen to a few hundred individuals, in environments with open skies, natural light, seasons, weather, the sounds of wind and water and animals. We're adapted to a planet. What happens when you take humans and seal them inside a metal cylinder for their entire lives? Not just for a few months like ISS astronauts, but forever, for generations, where the only sky is a painted ceiling, the only weather is climate control, the only wilderness is a carefully manicured park under grow lights. We don't actually know. We've never run that experiment, but we have troubling hints from analogous situations. Consider submarine crews. Nuclear submarines can stay submerged for months at a time, and the crews live in confined, isolated environments with no natural light, limited personal space, and constant proximity to the same small group of people. Psychological screening for submariners is rigorous, and even so, issues arise. Interpersonal conflicts, anxiety, depression, and what's sometimes called submarine syndrome, a collection of psychological symptoms including irritability, sleep disturbances, and difficulty concentrating. And submarine deployments last months, not lifetimes. Consider Antarctic research stations during winter. When the sun sets in March at places like the South Pole, it doesn't rise again until September. Researchers are confined to the station, unable to leave, completely isolated as even aircraft can't land in the extreme cold and darkness. Studies of these winter-over crews have documented psychological changes. Some people thrive, others struggle with depression, anxiety, interpersonal conflicts. And this is with highly selected volunteers who knew what they were signing up for, with satellite communications to stay connected to the outside world, with the absolute certainty that they'll return to normal life in a few months. Now imagine you're born on a generation ship. You never chose this. You had no say in the mission. The metal walls around you are the only world you've ever known. The same corridors, the same recycled air, the same 500 faces year after year. You can't leave, ever. There's nowhere to go. Outside is vacuum and radiation and death. You look out the windows and see only darkness punctuated by distant stars that never grow closer. The destination planet your parents and grandparents talked about, you'll never see it. You'll die aboard this ship, just like they did. Your purpose, your entire existence, is to maintain systems and raise children who will maintain systems and raise children, all for a goal that has no meaning in your lifetime. What does that do to a person? What does that do to a society? Some researchers have suggested that morale and mission commitment would inevitably decay over generations. The first crew, the volunteers who left Earth, they believed in the mission. They chose it. They said goodbye to their home world willingly. Their children might still feel connected to Earth through stories, through their parents' memories, through cultural traditions. But by the third or fourth generation, Earth is mythology. It's something from history, no more real than ancient Rome is to us. Why should they care about maintaining a mission that dead people from a world they never knew decided was important? You might see a shift in values. Maybe the inhabitants decide they don't want to continue to the destination. Maybe they want to turn the ship into a permanent home, wandering the galaxy indefinitely. Maybe they want to slow down or change course, but they can't. The ship's trajectory was set generations ago. The fuel budget doesn't allow for major course changes. They're locked into decisions made by people who've been dead for a century. That's a recipe for resentment, for psychological distress, for social breakdown. Then there's the issue of social structure and governance. How do you govern a closed society of 500 people for centuries? Democracy seems appealing, but what happens when the majority votes for something that threatens the mission? Do you have a constitution that can't be changed, rules imposed by the original crew that bind all future generations? That's fundamentally authoritarian. You're governed by the dead, by people who couldn't possibly foresee the situations you're facing. But if you allow complete self-determination, you risk mission failure. The generation ship governance problem is essentially unsolvable. Any system you design either constrains freedom to an unacceptable degree or allows for mission-threatening decisions. Consider conflict resolution. On Earth, if you have an irreconcilable conflict with someone, you can leave, you can move to another city, another country, you can cut ties. On a generation ship, you can't. You're trapped with that person forever. You'll see them in the corridors, in the dining halls, perhaps working alongside them for decades. Small grudges can fester into feuds. Feuds can split communities. In a population of 500, if the community fractures into hostile factions, the entire mission is jeopardized. Everyone must cooperate to maintain life support, to grow food, to repair systems. Dysfunction in social cohesion translates directly into dysfunction in survival capacity. And what about crime? On Earth, we have police, courts, prisons. We can remove dangerous individuals from society, locking them away or, in extreme cases, executing them. But on a generation ship, every person represents a fraction of your total genetic diversity, a fraction of your labor force, a fraction of your reproductive capacity. Can you afford to imprison someone for decades? That's wasted labor, wasted genetics. Can you execute someone for murder? You're reducing your population, potentially pushing it below viable thresholds. But if you can't effectively punish serious crimes, what deterrent exists? The social contract breaks down. Some theorists have suggested that generation ships would need to be designed with authoritarian control systems, perhaps even AI governance, to maintain order and mission focus across generations. But that raises profound ethical questions. Is it morally acceptable to condemn people to live under authoritarian rule simply because their ancestors volunteered for a space mission? The children born aboard didn't choose this life. They didn't agree to subordinate their autonomy to mission parameters. By what right do we impose that on them? This touches on a deeper philosophical problem that some ethicists have argued makes generation ships fundamentally immoral. If you send out a generation ship, you're creating people who will live their entire lives in confinement without choice for purposes they didn't consent to. On Earth, even people born into difficult circumstances have theoretical freedom. They can try to change their situations, migrate, rebel, make choices. But children born on a generation ship have no such freedom. Their destiny was chosen before they existed. They're instrumentalized, treated as means to an end, tools to carry a mission forward rather than ends in themselves. Philosopher Neil Levy has written about this, arguing that launching a generation ship might violate the basic ethical principle that we shouldn't treat people merely as means to others' ends. The original crew consented, but their descendants, they're brought into existence specifically to serve a function, and they can't opt out. It's a form of coercion across generations, and if we believe that freedom and autonomy are fundamental human rights, then creating a society where those rights are necessarily and permanently curtailed might be deeply wrong. But let's set aside the ethical concerns for a moment and return to the practical challenges. Because even if we solved the radiation problem, the life support problem, the psychological problems, and the governance problems, we still have more catastrophic failure modes to worry about. Let's talk about mechanical failures and accidents. Your generation ship is in essence a single point of failure. If something goes catastrophically wrong, there's no backup, no rescue, no second chance. And over centuries of operation, the probability of catastrophic failure approaches certainty unless your engineering is absolutely perfect, which it never is. Consider the propulsion system. Let's say you're using a nuclear fusion reactor, a technology we haven't even mastered yet, but which would be necessary for any realistic interstellar voyage. This reactor must operate reliably for centuries. It must be maintained by crews who didn't build it, using procedures passed down through generations, with spare parts that are finite in number. If the reactor fails catastrophically, you lose propulsion. You might also lose primary power, which means life support begins failing. Can you switch to backup systems? How long do those last? Can you repair the reactor without the industrial infrastructure of Earth? Or consider a collision. Space isn't perfectly empty. There are dust grains, microscopic particles, possibly even larger debris. At the velocities a generation ship would travel, even a tiny particle carries enormous kinetic energy. A dust grain the size of a pea hitting your ship at 10% of light speed would release energy equivalent to a large bomb. Your shielding would need to absorb and dissipate that impact. Most of the time it would, but over centuries, traveling through billions of kilometers of space, the probability of encountering something large enough to cause serious damage increases. And if you punch a hole in the hull, you have rapid decompression, loss of atmosphere, and potentially catastrophic damage to internal systems. What about fire? On Earth, fire needs oxygen, and when oxygen is depleted in an enclosed space, the fire goes out. But a generation ship is an oxygen-rich environment by necessity. If a fire starts, it could spread rapidly, consuming irreplaceable materials and equipment. Fire suppression systems exist, but they must work perfectly every time. A single failure could destroy critical infrastructure. And unlike on Earth, you can't just evacuate to safety and let the fire burn out. There's nowhere to evacuate to. Then there's the problem of system interdependence. On a generation ship, everything connects to everything else. Your food production requires water and power. Your water recycling requires power and spare parts. Your power generation requires cooling and maintenance. If one system fails, it can trigger cascade failures in others. Engineers design redundancy to prevent this, backup systems and alternative pathways. But redundancy adds mass, complexity, and points of failure. And over centuries, as components wear out and are scavenged to repair other systems, that redundancy erodes. There's also the specter of disease. Your generation ship carries a closed population of around 500 people, along with whatever microorganisms inhabit their bodies and the ship's environment. Humans are ecosystems. We carry trillions of bacteria in our guts, on our skin, in our respiratory systems. Most are harmless or beneficial. Some are opportunistic pathogens that can cause disease under the right conditions. You'd screen the initial crew carefully, trying to exclude people carrying dangerous pathogens. But you can't eliminate all microorganisms. You need your microbiome to survive. Over generations, the microbial ecology aboard the ship will evolve. Bacteria reproduce rapidly, with generation times measured in minutes or hours. In the time it takes for one human generation, bacteria experience millions of generations. That's enormous evolutionary potential. In the confined, unusual environment of a generation ship, with radiation exposure, with recycled everything, selective pressures will shape microbial evolution in unpredictable ways. You could see the emergence of antibiotic-resistant strains or entirely new pathogens adapting to exploit the unique conditions aboard the ship. If a dangerous pathogen emerges, you have limited options. On Earth, we contain disease outbreaks by isolating cases, by bringing in medical supplies and personnel from unaffected areas, by developing treatments using our vast pharmaceutical industry. On a generation ship, you have no outside help. Your medical supplies are finite. Your pharmaceutical manufacturing capability is limited to whatever small-scale facilities you built into the ship. If an epidemic breaks out, it could sweep through the entire population. With only 500 people, losing even a small percentage to disease could push you below viable population thresholds. And here's something truly chilling. What if the pathogen affects fertility or fetal development? Radiation-induced mutations could create bacteria or viruses that interfere with human reproduction. Imagine a pathogen that causes miscarriages or birth defects at high rates. Your population would collapse within a generation or two. The ship continues its journey, but the crew dwindles, ages, and eventually dies out, leaving empty bunks and silent corridors. Now let's talk about something researchers call cultural drift, and it's more dangerous than it sounds. Culture is how we transmit information across generations. It's not just art and music and traditions. It's technical knowledge, operational procedures, values, and mission commitment. On Earth, culture is relatively stable because we have massive populations, institutions dedicated to preservation, and written records. But even on Earth, knowledge is lost. Ancient techniques, languages, entire bodies of understanding have vanished because the chain of transmission broke on a generation ship. You have a tiny population and no external repositories of knowledge. Everything must be passed from generation to generation, through teaching, through mentorship, through written and digital records. But what happens when the experts die unexpectedly? What if the one person who truly understood the ship's navigation system is killed in an accident before fully training a replacement? What if crucial operational manuals are stored on digital systems that corrupt over time and nobody notices until it's too late? There's also linguistic drift. Languages change over time, especially in isolated populations. The English spoken aboard the ship might diverge significantly from Earth English over centuries. Technical terminology might shift in meaning. Future generations reading instructions written by the original crew might misinterpret them, not because they're careless, but because the language has evolved in ways that create subtle misunderstandings. A misunderstood instruction in a critical system could lead to catastrophic errors. Cultural values will also shift. The original crew valued the mission above all else. But their descendants, 10 generations later, might value personal freedom or artistic expression or spiritual pursuits that the original planners never anticipated. They might reinterpret the mission or reject it entirely. Remember, these are human beings with agency and autonomy, not robots. They'll develop their own philosophies, religions, social movements. Some of these might align with mission success. Others might undermine it. There's historical precedent for this kind of cultural transformation in isolated populations. Consider the Polynesian voyagers who settled islands across the Pacific. Some maintained seafaring traditions and continued exploring. Others, once settled, lost or abandoned their long-distance navigation capabilities. Within a few generations, knowledge that had taken centuries to develop was forgotten. On a generation ship, if future generations lose interest in maintaining the vessel or continuing the mission, there's no recovery. The ship becomes a drifting tomb, its inhabitants perhaps surviving for a while longer, but the mission effectively dead. Let's talk about genetic bottlenecks in more detail, because the numbers are even more disturbing when you dig deeper. We mentioned that you need at least 500 people to maintain genetic diversity under ideal conditions. But ideal conditions assume random mating, which never happens in real human populations. People choose partners based on proximity, personality, shared values, physical attraction. This assortative mating means that genetic mixing isn't random. Some lineages will have many descendants, others will have few or none. Over time, this creates unequal representation of the original genetic diversity. There's also the founder effect, a well-understood phenomenon in population genetics. When a small group breaks off from a larger population, they carry only a subset of the genetic diversity from the parent population. Whatever genes happen to be present in that founding group become the entire genetic heritage of all future generations. If the founders happen to carry recessive genes for hereditary diseases, those genes are now part of the permanent genetic landscape of your population. On Earth, harmful recessive genes are relatively rare in the general population because they're diluted across billions of people. If you carry a recessive gene for a genetic disorder, the probability that your partner also carries it is low, so your children probably won't express the disease. But on a generation ship with 500 people, the probability of both partners carrying the same recessive gene is much higher. As relatives become more common in the population over generations, the likelihood of harmful gene expression increases. The research team at the University of Strasbourg simulated this using their heritage model. They tracked specific genetic disorders across generations, modeling how founder effects and genetic drift would concentrate harmful genes. Their findings showed that even with 500 starting individuals by generation 8 or 9, you start seeing increased rates of genetic disorders. By generation 15 or 20, depending on radiation exposure and other factors, the population's genetic health has significantly degraded. And here's where it gets worse. Mutations aren't just creating new genetic problems. The loss of genetic diversity means you're losing evolutionary flexibility. On Earth, genetic diversity is what allows species to adapt to changing conditions. When environments shift, some individuals happen to have genetic variants that help them survive and reproduce in the new conditions. Over time, those variants spread through the population. That's natural selection, but with low genetic diversity, you have fewer variants to select from. If conditions change aboard the ship, if you encounter an unexpected environmental challenge or a new pathogen, your population might not have the genetic resources to adapt. You could face extinction, not because of any single catastrophic event, but because your gene pool lacks the variability necessary for survival. Think about it this way. Genetic diversity is like having insurance policies. Most of the time, you don't need them. But when disaster strikes, you're grateful you have them. A generation ship starts with minimal genetic insurance and loses coverage with every passing generation. Now let's discuss something that keeps mission planners awake at night: social breakdown and mutiny. History is filled with examples of expeditions that descended into chaos. The famous mutiny on the Bounty, where sailors rebelled against Captain Bligh. The Franklin expedition, where a British Arctic exploration mission ended in disaster, with survivors resorting to cannibalism. These weren't poorly planned missions. They were well-funded, well-equipped expeditions led by experienced commanders. But human psychology under stress is unpredictable. On a generation ship, stress is permanent. There's no relief, no shore leave, no return to normalcy. And if social cohesion breaks down, if factions form and conflict escalates, what happens? Do you have security forces, police, a military? Who controls them? What if they decide they should be in charge? What if a charismatic leader convinces a faction of the population to seize control of critical systems, to change the mission, to alter the ship's course or lifestyle according to their vision? You could design the ship with fail-safes, security systems that prevent unauthorized access to critical infrastructure. But those systems must be maintained by people. People who were born aboard the ship who might not share the original mission's values. If they decide the restrictions are unjust, they might disable or circumvent the security systems. And if conflict turns violent, if weapons are used in the confined spaces of a generation ship, the damage could be catastrophic. A hull breach during a firefight doesn't care about who's right or wrong. Some designs propose having no weapons aboard, but humans are tool users. Improvised weapons can be made from almost anything: a length of pipe, a sharpened piece of metal, chemicals from the ship's stores. Violence, if it erupts, can't be prevented by simply not including guns in the manifest. There's also the psychological phenomenon known as generational amnesia. Each generation perceives the environment they grow up in as normal, as the baseline. If conditions gradually degrade, if the ship slowly becomes less functional, less comfortable, each generation might accept the decline as simply the way things are. They don't realize that their grandparents had better air quality, more reliable systems, more variety in food. This normalization of decline can be insidious because it removes the motivation to fix problems. If you don't know things used to be better, you don't know they should be better. On Earth, we see this with environmental degradation. Older generations remember more abundant wildlife, cleaner rivers, larger forests. Younger generations, born into a more degraded environment, accept it as normal. They lack the frame of reference to understand what's been lost. On a generation ship, this could manifest as technical capabilities declining, knowledge being forgotten, systems degrading, all without anyone recognizing it as a crisis, because it's happening slowly enough that each generation adapts. By the time someone realizes the ship is in serious trouble, it might be too late. Critical systems might have degraded past the point of repair with available resources. Knowledge needed to fix them might have been lost generations ago. The population might have shrunk below viable thresholds. And the ship continues flying through the void, its inhabitants dimly aware that something is wrong but lacking the capacity to fix it. Let's shift perspective for a moment and consider the mathematical probability of success. Imagine every major system aboard the ship has a 99% probability of functioning correctly for each decade of the journey. That sounds quite reliable, doesn't it? 99% success rate seems like good engineering, but you have hundreds of major systems: life support, propulsion, navigation, power generation, thermal control, radiation shielding, food production, water recycling, waste processing, communications, computing, structural integrity. Let's say you have 200 critical systems, which is probably conservative. If each system has a 99% chance of functioning per decade, and you need all of them to function for a 250-year voyage, that's 25 decades. The probability that all systems survive is 0.99 to the power of 200 systems times 25 decades, which equals 0.99 to the power of 5,000. That's approximately 1.6 times 10 to the negative 22. Essentially zero. Your mission fails with near certainty. You might argue that systems have redundancy, that backup systems exist. Fair point. Let's say each critical system has a backup, and the probability that both the primary and backup fail in any decade is only 0.1% or 0.001. Much better. Now the calculation is 0.999 to the power of 5,000, which equals approximately 0.67%, or a 0.67% chance of total success. Still terrible odds. To achieve even a 50% probability of mission success with 200 critical systems over 25 decades, each system would need to have a failure rate of less than 0.00027 per decade. That's a reliability level we've never achieved with complex machinery operated continuously for centuries. It might be impossible with known physics and engineering. This is the tyranny of compound probability. Even highly reliable components, when combined in large numbers over long timeframes, create system-level failure probabilities that approach certainty. And these calculations assume independence of failures, that one system failing doesn't make others more likely to fail. In reality, failures are often correlated. A power system failure affects life support. A cooling system failure affects computing. Cascade failures multiply the risk. Some engineers propose designing generation ships with massive over-engineering, building in 10 times the redundancy necessary, using materials that last far longer than required, creating systems so robust that failure is nearly impossible. But this enormously increases mass, complexity, and cost. A ship over-engineered to this degree might be too massive to accelerate to useful velocities, or might require so much energy to propel that it becomes impractical. Now let's talk about navigation and course correction, because this presents yet another technical nightmare. You're traveling through three-dimensional space at velocities of thousands of kilometers per second, heading toward a star that's light years away. Your destination might be moving relative to your starting point. Stars orbit the galactic center, and their positions change over centuries. You need to update your course continuously based on precise measurements of your position and velocity. How do you measure your position in interstellar space? On Earth, we use GPS satellites. In near-Earth space, we can use ground-based tracking. But once you're light years from Earth, those methods are useless. You must navigate by the stars, using precise measurements of stellar positions and comparing them to your onboard database. This technique, called stellar navigation or astronavigation, is well established, but it requires extremely accurate instruments and constantly updated calculations. What happens if your navigation instruments drift out of calibration over decades or centuries? What if the computers running your navigation software experience hardware degradation, introducing subtle errors into calculations? What if future generations, maintaining these systems without fully understanding them, make small mistakes that compound over time? A tiny navigation error early in the journey could mean missing your destination by astronomical distances, and course corrections require fuel. Most propulsion systems can't simply stop and restart at will. If you're using a continuous thrust system, any change in velocity requires expending reaction mass, fuel that you can't replace. Your fuel budget was calculated centuries ago based on a specific trajectory. If you need to make unplanned corrections, you're drawing from reserves meant for deceleration at the destination. Use too much fuel correcting your course, and you might not be able to slow down when you arrive. You'd shoot past your destination planet at thousands of kilometers per second, unable to stop, condemned to continue into the void until your ship becomes a derelict. This brings us to the question of what happens when the ship actually arrives at the destination, assuming it does. You've spent 250 years traveling to an exoplanet that telescopes from Earth identified as potentially habitable. But telescope observations, even with advanced instruments, can't tell you everything about a planet. They can detect atmospheric composition, estimate temperature ranges, gauge planetary mass and size. But they can't tell you about surface conditions in detail, about microbial life that might be deadly to humans, about atmospheric chemistry that might be toxic despite containing oxygen. What if the crew arrives and discovers the planet is uninhabitable? Maybe it looked promising from Earth, but up close it has some deal-breaking problem. Maybe the atmosphere contains trace gases that Earth-based analysis missed, gases that would poison humans over time. Maybe the surface is covered in microorganisms that aggressively attack organic matter, making settlement impossible. Maybe the planet's magnetic field is too weak, exposing the surface to dangerous radiation levels. The crew has no backup plan. They can't go home. Earth is 250 light-years behind them now. Even if they could reverse course, which they probably can't with their remaining fuel, another 250-year journey would bring them to an Earth 500 years older than when they left. Everyone they knew is dead. The civilization they left might not even exist anymore. They're stranded in an alien star system with nowhere to go. Or consider this scenario. The planet is habitable, but only barely. It requires extensive terraforming or the construction of sealed habitats. The crew has been living in artificial environments for generations. They've lost much of their technical knowledge. Their population has declined due to genetic problems and radiation exposure. They're exhausted, psychologically damaged, perhaps fragmented by internal conflicts. Do they have the resources, the knowledge, the cohesion to establish a viable colony? Or do they land on this new world only to slowly die out, unable to adapt, unable to build, the last survivors of a failed experiment? There's a concept in astrobiology called the Great Filter, proposed by economist Robin Hanson. It's an attempt to explain the Fermi paradox, the question of why we haven't detected any evidence of alien civilizations despite the vast number of potentially habitable planets in the galaxy. The Great Filter hypothesis suggests that somewhere between the emergence of life and the development of spacefaring civilizations, there's a barrier, a filter that prevents most life from advancing. Maybe the filter is behind us. Maybe it's rare for life to emerge or for intelligence to evolve. Or maybe the filter is ahead of us. Maybe becoming a true interstellar species is so difficult that almost no civilization manages it. Gelation ships might be proof that the Great Filter lies ahead. Maybe the engineering challenges, the biological problems, the psychological stresses, the sheer statistical improbability of maintaining a closed system for centuries all combine to make interstellar colonization effectively impossible. Maybe every civilization that tries eventually realizes their generation ships become tombs, drifting silently through the cosmos as testaments to ambition that exceeded capability. But let's step back from the darkness for a moment and consider whether there are solutions. Could we engineer our way out of these problems? Could advanced technology, perhaps technologies we haven't invented yet, make generation ships viable? Some researchers argue yes, that many of these challenges are temporary limitations rather than fundamental barriers. Let's explore those optimistic scenarios and then examine whether they truly solve the underlying problems. First, the genetic diversity problem. Some propose using frozen embryos or frozen gametes, eggs and sperm preserved cryogenically, to supplement the genetic pool. Instead of starting with 500 people, you start with 500 people plus thousands of frozen embryos representing diverse genetic lineages from Earth. When the population needs genetic refreshment, you thaw and implant embryos, introducing new genetic diversity without increasing the initial crew size. This is sometimes called a seed ship variant. The concept is clever. Embryo freezing is established technology. We've successfully frozen and thawed human embryos for decades. The success rates are good. Storage requires liquid nitrogen or advanced cryogenic systems, but these could theoretically be maintained aboard a generation ship. You'd need artificial wombs or volunteer surrogates from the existing crew to bring the embryos to term, and you'd need to carefully manage the genetic introduction to maximize diversity benefits. But here's where it gets complicated. Those frozen embryos would be born into a society that's existed for generations aboard the ship. They'd have no biological parents among the crew. They'd be outsiders, genetically different, raised by people who might view them as somehow other. Human societies have a long history of treating outsiders poorly, of creating in-groups and out-groups. Would these children be fully accepted? Or would they face discrimination, isolation, reduced mating opportunities? If they're marginalized, they don't effectively contribute to genetic diversity. The genes are there, but they're not mixing into the population as intended. There's also the question of who decides when to thaw embryos and how many to thaw. Do you have a schedule set by the original mission planners? Do future generations decide based on population needs? What if they decide they don't want to thaw any more embryos, that they want to keep the population smaller, that they reject the idea of bringing in genetic outsiders. The frozen embryos give you genetic potential, but actualizing that potential requires cooperation across generations, and you can't guarantee that. Another proposed solution is genetic engineering. What if we could modify the human genome to make people more resistant to radiation, more resilient to the psychological stresses of confinement, longer lived, more fertile? Technologies like CRISPR have made precise genetic editing feasible. We could theoretically create humans optimized for generation ship life. This opens enormous ethical questions. Are we creating a subspecies of humans genetically distinct from Earth humans, specifically designed to live in artificial environments? What rights do these engineered individuals have? Who consents to their modification? They don't exist yet, so they can't consent. Are we playing God, fundamentally altering what it means to be human for the convenience of a space mission? And there are practical concerns beyond the ethics. Genetic engineering can have unintended consequences. Genes interact in complex networks. Changing one gene can have ripple effects throughout the genome. A modification that increases radiation resistance might inadvertently affect cognition or fertility or immune function. We wouldn't know until the engineered individuals are born and mature, and by then it's too late. You can't recall a genetic modification like you'd recall a defective product. It's permanent and it propagates to all descendants. Some futurists propose abandoning biological humans entirely. Instead of sending people, send artificial intelligence, robots, or uploaded human consciousnesses, digital copies of human minds running on computers. These don't need air, food, or radiation shielding beyond what's necessary to protect the computer hardware. They don't experience psychological stress from confinement. They can be backed up, so individual failures don't threaten the mission. This is sometimes called a post-biological approach to space exploration. It's an interesting idea, but it sidesteps the fundamental question. If you're sending machines, you're not really establishing human presence in the stars. You're establishing machine presence. Maybe the machines will build habitats and create biological humans once they arrive, growing them from genetic templates or frozen embryos. But those humans would have no connection to Earth except abstract genetic heritage. They'd be born in an alien environment, raised by machines, with no human culture or history except what's been preserved digitally. Are they really a continuation of humanity, or something new? And we're assuming that artificial intelligence can actually replicate human consciousness, that uploading minds is possible, that digital entities can have experiences and motivations analogous to biological humans. These are enormous assumptions. We don't actually understand consciousness. We don't know if it can be uploaded. The entire concept might be based on a misunderstanding of what minds are and how they work. Let's consider another approach: generation ships with much larger populations. Instead of 500 people, what if you sent 50,000 or 500,000? With a larger population, genetic diversity is easier to maintain. You have room for specialization, for preserving knowledge across redundant experts. Social structures can be more complex and resilient. Psychological issues might be reduced because people have more social options, more diversity of experience within the ship. But the engineering challenges scale brutally. A ship for 50,000 people needs roughly 100 times the life support capacity, living space, food production, and resources. It needs to be vastly larger. The mass increases proportionally, maybe more than proportionally, because structural requirements scale unfavorably. You need stronger structures to support larger vessels. The energy required to accelerate this massive ship to interstellar velocities becomes astronomical. We're talking about energy expenditures that might exceed the total energy production of current human civilization for decades or centuries. Where do you get that energy? Nuclear fusion might provide enough power density, but we haven't achieved sustained fusion power generation yet, much less scaled it to the levels required for accelerating ships massing millions or billions of tons. Antimatter would provide even higher energy density, but we can produce antimatter only in microscopic quantities at enormous cost. Producing the antimatter fuel for a giant generation ship might require centuries of production, using facilities we haven't built yet, and you still haven't solved the fundamental reliability problem. A larger ship has more systems, more components, more failure points. Yes, you can build in more redundancy, but you've also increased complexity. The maintenance burden is proportionally larger. You need more people working on maintenance, which increases the required population, which increases the ship size, which increases the maintenance burden. It's a spiral. Some designs propose not a single giant ship, but a fleet of smaller ships traveling together, maintaining communication and cooperation. If one ship experiences catastrophic failure, the survivors could potentially transfer to other ships. The fleet as a whole has resilience that a single ship lacks. This is called a convoy approach. It's more robust in some ways, but it introduces coordination challenges. The ships must maintain formation across light years, matching velocities precisely. They must communicate constantly, sharing resources and information. What happens if ships drift apart, if communication fails, if one ship decides to alter course independently? You've fragmented your mission, and you've multiplied the engineering challenge because now you need to build and launch multiple interstellar vessels, each fully capable of supporting its population. There's also a concept called the world ship, a generation ship so large it's essentially a mobile habitat, a hollowed-out asteroid, or a purpose-built megastructure kilometers across, housing not hundreds or thousands but millions of people, a complete society, a nation in space, with room for cities, forests, lakes, diverse ecosystems. At that scale, you approach something resembling a small planet. Genetic diversity is no problem. Cultural preservation is easier. Psychological issues from confinement might be minimal because the environment is so large and diverse. But world ships are purely theoretical. The engineering is beyond anything we can currently imagine building. The energy required to move such a structure at interstellar velocities is staggering. The construction would take centuries and require resources from entire solar systems, and you still face the same fundamental challenges of maintaining a closed system for centuries, just at a larger scale. Larger doesn't eliminate problems. It sometimes just hides them better. Perhaps the most philosophically interesting proposed solution is the sleeper ship, where the crew spends most of the journey in suspended animation or cryogenic sleep. You'd only need a skeleton crew awake at any given time to monitor systems, or perhaps you'd automate everything and wake nobody until arrival. This eliminates most of the psychological problems, the generational issues, the cultural drift. The people who leave Earth are the same people who arrive at the destination. Suspended animation appears frequently in science fiction, but the reality is brutally difficult. We can freeze human embryos successfully. We can freeze and thaw certain tissues and organs with reasonable success rates, though damage still occurs. But freezing and successfully reviving a complete adult human, we've never done it. Not even close. The problem is ice crystal formation. When you freeze biological tissue, water inside cells forms ice crystals. These crystals expand, rupturing cell membranes and destroying cellular structures. You can use cryoprotectants, chemicals that reduce ice crystal formation. but these are toxic at the concentrations required to fully protect tissues. The damage from the cryoprotectants competes with the damage from freezing. Some researchers are exploring vitrification, a technique where tissues are cooled so rapidly they form a glass-like solid without ice crystals. This works for small samples, even for some organs, but scaling to whole-body vitrification presents enormous challenges. You need to perfuse every tissue with cryoprotectants uniformly and cool the entire body at extreme rates. The larger the organism, the harder this becomes. And even if you successfully vitrify someone, you then need to warm them evenly without causing thermal stress that damages tissues. Uneven warming creates thermal gradients that can crack vitrified tissues like breaking glass. Let's say we solve the freezing problem. We develop technology that can successfully freeze and revive humans with minimal damage. You still face other issues. Frozen bodies must be maintained at cryogenic temperatures for centuries. This requires continuous power. If power fails, temperatures rise and your frozen crew begins to degrade. You might have backup power systems, but over centuries, the probability of total power failure becomes significant. And unlike awake crew members who could respond to emergencies, your frozen crew can't wake themselves up to fix problems. There's also radiation. Cosmic rays don't stop just because someone is frozen. Radiation damage accumulates in tissues over time. A frozen crew member exposed to cosmic radiation for 250 years would accumulate significant cellular damage, increasing cancer risk dramatically if they're revived, potentially making revival impossible if damage is too extensive. You'd need heavy radiation shielding around the cryogenic storage, adding mass to the ship. And here's a darker thought. What if the automated systems wake the crew at the destination, but something has gone wrong during the journey? Maybe the ship's trajectory was off, and you're not where you expected. Maybe systems degraded during the voyage, and the ship is barely functional. Maybe the destination planet turned out to be uninhabitable. The crew wakes up to discover they're in an impossible situation, with no time to adapt, no generations of cultural development to prepare them psychologically. Just sudden, catastrophic realization that the mission has failed. Some designs combine approaches, using both awake crews and sleepers. You have a small rotating crew that handles maintenance and monitoring, serving in shifts measured in decades, while most of the population sleeps. This reduces the psychological burden on any individual, spreads the maintenance workload across multiple generations, but still maintains a larger genetic pool and preserves the original crew for arrival. But now you have hybrid challenges. The awake crew ages and dies while the sleepers remain young. Psychological adjustment to being left behind while your friends sleep for centuries could be devastating, and you still need to solve the technical problems of both generation ships and sleeper ships. You haven't eliminated challenges. You've combined them. Let's talk about propulsion more deeply, because the speed of your ship fundamentally affects every other problem. If you could travel faster, journey times shrink, and many issues become more manageable. A journey that takes 25 years instead of 250 years requires only one generation, maybe two. Genetic drift becomes less severe. Mechanical systems need to last decades instead of centuries. Radiation exposure is proportionally reduced. The problem is acceleration. To achieve high velocities, you need enormous energy. The kinetic energy of a moving object increases with the square of velocity. Doubling your speed requires 4 times the energy. Increasing speed tenfold requires 100 times the energy. And you need to accelerate not just the payload, but also the fuel you're carrying for deceleration at the destination, which means you need even more fuel for acceleration, which means more mass, which requires more energy. This is the tyranny of the rocket equation. Chemical rockets are completely inadequate for interstellar travel. The exhaust velocities are too low, and the energy density of chemical fuels is insufficient. Nuclear propulsion offers better performance. Nuclear pulse propulsion, where you detonate nuclear bombs behind the ship and ride the shockwave, was seriously studied in projects like Orion in the 60s. It could theoretically achieve velocities of a few percent of light speed, but it requires thousands of nuclear devices, raises obvious safety and political issues, and still leaves you with journey times measured in centuries for nearby stars. Fusion rockets would be better, offering higher exhaust velocities and using fuels like deuterium that are relatively abundant. But we haven't achieved controlled fusion for power generation yet, much less weaponized it into a rocket engine. Magnetic confinement fusion, inertial confinement fusion, these are technologies that have been perpetually 30 years away for the last 50 years. Maybe we'll crack it, maybe we won't. Antimatter rockets would be ideal from a physics perspective. Matter-antimatter annihilation converts mass directly to energy with perfect efficiency, offering the highest possible energy density. A matter-antimatter rocket could theoretically accelerate to substantial fractions of light speed, but producing and storing antimatter is absurdly difficult and expensive. Current production rates measure antimatter in nanograms per year, and it costs billions of dollars per gram. Producing the tons of antimatter required for an interstellar mission would require energy expenditures and timescales that are difficult to comprehend. Some designs propose using external power sources, a laser propulsion system, where enormous lasers based in the solar system beam energy to your ship's light sail, pushing it to high velocities without carrying fuel. This was the concept behind the Breakthrough Starshot initiative, which proposed sending tiny probes to Alpha Centauri at 20% of light speed using ground-based lasers. It works for tiny probes, maybe, though even Starshot faces enormous technical challenges. But scaling to a generation ship, massing thousands or millions of tons, the laser power required would be astronomical, measured in terawatts or petawatts. You'd need solar arrays the size of continents or fusion power plants beyond our current capability, and the beam must track the ship across trillions of kilometers with extreme precision. Any misalignment and you're not pushing the ship effectively, or worse, you're heating parts of the structure dangerously. And here's the kicker with laser propulsion. It can accelerate you, but how do you decelerate at the destination? You need another laser array at the destination star system to slow you down, but there's nothing there. You'd have to send it ahead of time, which creates a chicken and egg problem. Or you'd need to carry your own deceleration system, which means carrying mass, which reduces the advantage of laser propulsion. Some truly exotic proposals involve manipulating space-time itself, warp drives, where you compress space in front of your ship and expand it behind, theoretically allowing faster-than-light travel without violating relativity because you're not moving through space, you're moving space itself. This comes from Miguel Alcubierre's 1994 paper on warp drive metrics. It's mathematically consistent within general relativity, but it requires exotic matter with negative energy density, something that probably doesn't exist and definitely can't be produced in macroscopic quantities with known physics. The energy requirements might exceed the total mass energy of the observable universe, and there are causality problems, potential for creating closed time-like curves, violations of fundamental physics. Warp drives are fun to think about, but they're almost certainly impossible. Wormholes, hypothetical shortcuts through space-time connecting distant points, face similar problems. They'd require exotic matter to keep them open, assuming they can exist at all. And even if you could create and stabilize a wormhole, you'd still need to get one end of it to your destination, which means sending it there slower than light, which brings you back to the original problem. The brutal truth is that with known physics, with even optimistic projections of future technology, interstellar travel is monstrously difficult. Generation ships represent perhaps the most realistic approach, and as we've explored, they're fraught with potentially insurmountable challenges. If the challenges of generation ships weren't terrifying enough, click the video on the screen to understand what deep space itself does to the human body and mind. After everything we've just covered, you need to see what happens when humans actually venture into the void.